Hello, sir. It's good to have you here. We are on live stream. Assalamu alaikum. Hello, Tyler. Good to see you. So Tyler, are you able to hear me clearly?
I'm sorry.
Are you able to hear me clearly?
Yeah. Yeah.
Sweet. Hey, Trevor,
Hey,
how are you?
I'm doing well. Am I supposed to be in the Zoom room or just watching from the YouTube stream?
You're from UT, and I think pretty much who is a part of UT is supposed to be on the Zoom call, so don't worry.
Okay, cool.
Yeah. Who's your mentor, Trevor?
Minsu.
Okay, nice.
Yeah, we met. He just
Okay,
wasn't able to make it to the mentor
okay.
kickoff.
Mm-hmm. That's pretty cool. So how is it going? Are you in Austin?
No, I'm in the Dallas-Fort Worth area.
Okay, nice, nice.
What about you?
I am traveling in California.
Oh, I see.
Yeah,
Nice.
so it happened. So yeah. Anyways, okay. So yeah, today Beau is going to join us soon, and let's see how that goes. And yeah, how about you, Tyler? How are you doing?
I'm doing good. I just got the Pfizer vaccine yesterday.
That's pretty cool. Let me know how that goes, like in a long run. So yeah, on 29th, it was supposed to be open for all Texans, right?
Yes. And so what ended up happening is I went through Austin Public Health because you can it's almost like a lottery. Me and my girlfriend did that. And we couldn't get in because all the 1,200 doses, just everybody was when 7:45 hit, it was just gone. So we went on this vaccine finder and everything was taken up almost instantaneously. But HEB has the only website that refreshes live. So we just hit refresh over and over again and tried to click through as quickly as possible to try to find vaccines close. And after 3.5 hours, we were able to find one. We were able to get, because the thing is, you click through it and somebody else is tons of people were doing this. So it's just taken instantaneously. So after about 3.5 hours, we were able to get one close. So we both
That
did
is so
that
cool.
yesterday.
I think Pfizer is pretty good. AstraZeneca had some problem recently regarding blood clotting, but I think now they have removed I'm not sure if they have removed the ban in Europe, but people have started to use AstraZeneca. But Pfizer is good, I think. So
yeah, Pfizer and Moderna are the best, it seems.
nice, nice. Congratulations on getting vaccinated. You're the only, healthy, non older person who got the vaccine, which I know. Yeah.
Yeah. Well, yeah, I mean, I had to just click through really quickly. We optimized all the keystrokes to try to get the appointment as quickly as possible. It was crazy how competitive it was. We learned a lot of different cities in Texas in the process, though.
Interesting.
So
I believe I might get
close these were.
Yeah, I might get one soon. I'm not sure. I will get one, but in a matter of few days. I'm not sure how the public health system of Lubbock is working, but let's see how that goes. I wish I was in Austin.
Yeah, Austin does the lottery twice per week, Monday, and then people cancel their appointments throughout the week. So then Thursday is for all the appointments that people canceled basically from Monday. And so basically they release everything at, I think it was 7:45 p.m. But I got in around My girlfriend got in at like exactly at 7:45. I clicked it at like 7:46 and everything was gone at 7:46. And then she got in to like try to get an appointment, but then was beaten. Everything was taken up when she got the portal and said, here's your appointment time, click this appointment time, and it was already gone by the time she hit confirm. So it's like crazy. People are like going super fast.
Makes sense. I mean,
Yeah.
It's more valuable than gold right now.
Yeah.
So that's pretty cool. Are you planning to get vaccinated, Trevor?
Yeah, I have it. I have something scheduled.
Nice. Yeah, I'll get one once I go back to Lubbock, probably.
It's interesting. I was just thinking, and like, I don't know a whole lot about like the situation, but all of these like local municipalities basically have to build highly concurrent systems. And I feel like that's definitely a challenge that requires at least a base level expertise in building concurrent systems. But I just kind of found that interesting because I feel like a lot of the smaller municipalities may not have the technical resources to build those things in a short period of time. But maybe I'm misunderstanding everything.
Well, yeah, I think that HEB, like, they have some central software engineering team that takes care of it. In fact, Afzal, Lubbock, because I was seeing like basically live all the appointments. Lubbock on HEB's website, if you basically do what I did, you should be able to get one in Lubbock pretty quickly, honestly, because like people would. It's not like Austin. It's like you click it, it's gone. Lubbock would have some appointments hang out for like 15 seconds and they would pop up from time to time. So, I mean, if you have a 15-second window, you just click and you can beat everybody. But Austin's like crazy. They're gone in like half a second. So we drove about an hour away to Temple, Texas to get our vaccine. And then we have to go back there to get our second one here in a couple weeks.
Hello, folks.
Hi, Andrew.
Hey, how are you? Good. Is this Tyler?
Good. Yeah.
Awesome.
Hello, Andrew.
So are you a colleague of Beau's?
Yeah. So basically, I'm the business manager at ARM for the HPC tools. And Beau is actually, for today, he's like the more important guy. I'm just kind of listening on. I handle North America I tax one of my accounts. So I'm interested in what's being talked about today.
Good to have you here, Andrew.
Oh, thank you. Very nice to meet you, Mohammed.
Yeah. So yeah, I'm doing good. How about yourself?
I'm doing well, great. I mean, I heard you guys briefly talk about vaccines, and I'm gonna get my first one next week, so I'm pretty excited about that.
Are there any after effects, Tyler, since you got this shot recently?
I haven't felt anything. My girlfriend felt a bit dizzy yesterday. She took like a 2-hour nap because she felt like tired, but now she feels fine. My mom got the Moderna. So we both got Pfizer yesterday. My mom got Moderna and she really didn't have much even on either dose, my mom or my dad. My sister got the Moderna on Monday. Me and my sister, basically, we both just went crazy and like did the whole competitive, like we're going to try to get the slot. So we both got it very early. She said she got like chills. She felt like very cold when she was trying to sleep after the Moderna. That was about 12 hours afterwards, but now she feels fine. That's after the first dose.
Mm.
But my mom said she didn't feel anything from either dose, really.
Interesting. Yeah. Let's see how fast we all get vaccinated, honestly. Right now it's lottery based. I hope it sorts out pretty soon.
Yeah, I think Beau just came in.
Yeah, Beau looks like he arrived. Hey, Beau.
Yeah, we're here. Howdy.
All right.
Hello, Beau.
Hey, Mohammed, how are you doing?
I'm doing good. How about yourself?
Good, good indeed.
So
it's right about 12 o'clock. Should we start now or should we wait a few minutes for more folks to join?
So it's generally like we all have classes till 11. So I'm pretty sure a lot more people will join in next 5 minutes.
Okay. Well, Beau, we have plenty of time to cover this material. So I imagine 5 minutes isn't that big.
We do. I think part of it, Andrew, and Mohammed, we can kind of handle any way you want to, was to have a pretty broad Q&A discussion, not just about the tools, but maybe about HPC industry and kind of that type of stuff. Is that also on the agenda?
Exactly. And also about the skills required and, any opportunities you think are pretty hot in your field, things like that. I think that would be really helpful for people who have joined, in addition to the tools you are going to talk about. Yeah.
So I'm kind of thinking we'll kind of go through a brief PowerPoint overview of what's what. So for folks that don't know what our tools are about at all, and then something of a hands-on demonstration of DDT map and performance reports. And the total time frame for that will probably be less than an hour. And I think we budgeted an hour and a half or so. So in terms of the tools, questions about the tools, I encourage folks to just interrupt as we're going along or type it into chat and Andrew will interrupt me. And then in terms of kind of career advice stuff, once we've kind of wrapped up the product demo, we should still have a good half hour or so for that. Does that all sound good?
Yeah, that sounds great. And yeah, with this, I would like to introduce you to a few people who work with me at SIAM. So
Great.
we have Tyler here, who's our industry liaison.
Howdy.
And Meghna, who's the vice president of the SIAM chapter here at UT.
Hi.
Hello.
And Evan, who is our who's our event coordinator, who helped, with organizing this event.
Hey, nice. Yeah.
And Gopal, who's our senior advisor.
Hello.
Yeah, that's us, and we are really happy to have you here at UT Austin. Like, did you ever get a chance to come visit UT, Beau or Andrew?
Yeah, we do. So our one of our main offices that is for ARM is in Austin. Obviously, it's been a while since we've been there, but we visited there. And also, TAC is a significant customer for us. And in normal times, we'd usually get there once or twice a year to visit our customer at TAC.
Well, the other thing too, I mean, it's just down the road. I mean, it's somewhat related, I guess. But a few years ago as well, and Beau will end up talking about this during today's discussion, but we're increasingly seeing more Python used in conjunction with the HPC. So we've actually have started to tailor our tools for enhanced Python support. And we were actually at SciPy, I think 2 years ago, maybe 2019, I forget.
Summer 19.
In Austin. So we were downtown, I think at the AT&T Center or something of that nature.
That is pretty awesome. So did you like Austin City?
I like it, except on the hot times. When we were there in July, it was the order of 100.
That sucks.
Yeah, that's a little tough, but a nice city.
It's great in March. It's wonderful in the March-April timeframe, but I have to say, when we were there in July and I was wearing a suit and it was over 100 degrees with the humidity, I'm looking around just thinking to myself, how did the city exist before there was air conditioning?
Yeah.
It's amazingly hot.
Yeah, it can be hot sometimes, but yeah, I mean, most of the times it's pleasant. So compared to other cities in Texas, the Texas can be really hot.
Oh yeah, no, it's a great city, and we were also there for SC. I believe that was in 2015, Beau. I think the last time.
Yeah, that sounds about right. It's been a few years.
Yeah.
Fun city for a big conference, yeah.
Sweet. If anyone would like to chat with Beau or Andrew beforehand, you can go ahead and unmute yourself or type in the chat. Feel free. And me and Beau had a few like discussions over email as well as in the oil and gas HPC. So he's a nice person to talk to. So I would really, really recommend people who'd like to, talk to Beau directly. You can do that right now.
I was just curious about, I was just curious about the mention of Python being used in HPC. I know that kind of like the stereotypes I've heard is that, Python is like up to 1,000 times slower than C and all these other things. But I was wondering, what is driving the increase in Python code being used on HPC systems?
I think there's several variables that are driving it of much like a lot of higher level languages, it's making it much easier for computational scientists to kind of prototype code. So there's a few different uses. We see uses where people are using Python to create something of a prototype. It's going to be a code that's not, a large production code. It's closer to a prototype. And the other part of it, which I find really exciting, is for my whole career, anyone in this field has, been a background in mathematics and physics or biology, what we might call the hard sciences. Python is really opened it up to a lot broader group of users. So we're seeing people in finance, for example, so like MBA type folks that might not have quote a hard science background, but definitely quantitative people. At SciPy, we saw some amazing presentations of people that are like history professor researchers that have some quantitative needs, and they're able to use Python to do some quantitative analysis where if it was in Fortran and C, it just really wouldn't happen. So I think there's several drivers of opening it up to additional users, which means growing the market, new opportunities, and also for just kind of quick and dirty stuff. So we have a lot of customers that are kind of on the research end of the spectrum, and it enables it to be much quicker. And to your comment of it can be thousands of times slower. If you write everything in native Python, that's certainly true. But I think there's a lot of toolkits that are enabling performance. So for example, NumPy on the host or Cuppy on a GPU, things like pandas, a lot of numerical toolkits where they've done a lot of the performance and they've optimized it for the architecture. Now, overall, it's going to be pretty hard pressed to have a native Fortran code that's not faster than something that's a hybrid of Python. But I think when you kind of design your code well and you use these toolkits, you're still losing maybe a couple factors of performance. So, not acceptable for a large production code, but for something that's relatively small, kind of a prototype oriented thing, a couple factors of performance to be able to get something out much quicker is kind of worth a trade-off still. And I think it's going to get better. In fact, Guido Nystrom, the Python original author, was a guest speaker at an internal event recently. And one of the things that they're making a priority going forward, which Microsoft is funding and behind, is getting the native interpreter much faster. So kind of that bridge between it, I think, is going to get better. It'll never be the same. Obviously, writing a native Fortran code is always going to be quicker, but I think the gap is shrinking and enabling a lot more people to get into it.
And just to kind of add to that a little bit too, as well, is that it's amazing in terms of the amount of people now that are organizations that are starting to look at using Python within HPC. We just recently spoke to a national lab that 2 years ago said we'd never use Python. And we brought it up probably 2 or 3 weeks ago. And Beau, I forget what the percentage is, but he said that they're now bringing on users that are using Python. So even the big labs are dabbling in it, which I find really interesting.
Thank you for the insight. I think just to add a bit to that, coming from like a neuroscience background, I know that a lot of the neuroscience labs are kind of pushing for moving from MATLAB to Python. So they're kind of seeing Python as the future, I guess, at least for now. But yeah, that's pretty interesting.
Cool. With that, I think now is the time to start the presentation. Thank you, Trevor, for your question. So, hello and welcome, everyone. I'm Mohammad Afzal Shadab, and I'm the president of SIAM chapter at UT. And today, I'm going to present you ARM, and the representative from ARM is Dr. Beau Paisley. He's a solutions architect at ARM, and we also have Mr. Andrew Westergen, and Beau will talk about. He's going to provide an overview of ARM, which is a cross-platform integrated environment for debugging and optimizing parallel codes at any scale. And he's going to live demo some of the tools which he's been using, and he has actually developed at ARM. Moreover, he's going to talk about the role of computational scientists in HPC industry, as well as talk about some of the opportunities at ARM. So with that, I'd like to call and welcome Beau. Beau, up to you.
Awesome, great, thanks you, Mohammed. So we're going to start with an overview of the tools and a little bit of demo. And in terms of questions, I really encourage you to interrupt with questions as I'm going along. If you prefer to enter your question in chat, that's fine also, and I'll ask Andrew and Mohammed to keep a lookout for things in the chat window and interrupt me in real time, kind of best with that. And then kind of at the end would probably be the best time. We're gonna have plenty of time of more general HPC career type questions. All right, find my presentation. All right, so Forge. So our toolkit is called Forge, and this is the integration of our debugger DDT, our source code profiler map, and our application profiler performance reports. So it's just kind of the bundling of these tools. Now, one thing I'd like to point out is we're cross-platform. We run on x86, Power, and ARM architecture, and we support CUDA GPUs. We were actually kind of something of a startup that was acquired by ARM about 4 or 5 years ago, but we still support all major platforms. And this is just kind of the workflow that our tools support. So it's just the iterative, create your code, run, analyze, debug, and our tools are really optimized to support this HPC workflow and very much designed from the ground up, both in terms of user interface and architecture to support large-scale HPC codes. We typically run on dozens, hundreds, and thousands of processes, and we've been frequently used at like full scale on a lot of very large supercomputers, so hundreds of thousands of processes. So these are just some of the highlights for our debugger DDT. Spark lines, it's kind of the scalable print statement. This is the ability to see the value of variables across many processes. Watch points, the ability to halt execution dependent upon the value of an expression. So really useful when you get to a point in the code where the state of things is not as you expect. Set a watch point and locate the error. Static analysis. So one thing we do before we actually even run in earnest is when you load the source code into the environment, we do some static analysis for things like unused variables, using variables that haven't been assigned a value. Essentially anything that can be detected semantically without executing the code, the debugger will give you some insights about that so you can see it before you even run. Memory debugging, so the ability to detect errors of reading or writing outside of an array. Heap-related problems of like dangling pointers, using freed memory, failing to free memory, inspecting allocations, that type of thing. So you kind of detect the state of memory in your execution. And one thing I like to point out in this is a lot of folks are using the Intel compilers at this point, probably by far the most used production compiler that we see among customers. And Intel has a lot of great features for detecting these type of issues. So for example, you can turn on detection of reading or writing outside of an array. And the compiler does a great job of that, but it's very expensive, easily many factors of performance, where doing that in the debugger is much less overhead. So I really encourage you, if you are using that feature, not saying to stop using it, but try it in the debugger first and save some of your performance. All right, so code optimization. So I like to kind of present kind of the workflow that we prescribe. So in-depth tutorials, we really spend a lot of time on more focused on best practices beyond just the tool features themselves. And it's really important when you're optimizing to kind of follow the workflow, because it's really easy to jump to the wrong step. So for example, I frequently encounter customers where they'll say, well, geez, I think I can get better vectorization out of this code. And we profile it and find there's some terrible communication patterns or terrible IO issues. And in vectorization, you might get a factor of 2 or 4, or maybe on a modern processor, even a little bit more. But the order of problems in IO or communication would be much, much larger. So very important, whenever you go to optimize, profile first and make sure you're focusing on the low-hanging fruit, the best opportunities. So the first tool for doing that is our application level profiler performance reports. It just generates a single page, simple report, very low overhead. You can also run it on production codes. You don't need symbols, but you definitely want to have optimization turned on. So have optimization turned on at whatever level you intend to deploy at. And the tool generates this very simple report where it shows at a high level how time is being spent. So we'll show the percentage of time spent within compute. And if you have GPUs available, it'll break down and show the time spent within GPUs, time spent within MPI, and then at the bottom, it breaks that down. So very easy to see at a high level how time is being spent. And one thing we can do in performance reports is apply some heuristics to give some kind of objective advice. So for example, if you run a job with a lot of nodes and each node is not using much memory, it might be a case that you can run fewer processes with larger problem sizes on each node and get better throughput. So this really is a starting point, and also useful for both developers and kind of system level people. So for example, at large sites, system admin type folks that want to see that the cluster is being well used, we'll get a performance report for the run to make sure that users are running a good configuration. A classic one I like to think of is I worked at NCAR, and the default build for Wharf was with optimization turned off for a period of time. And scientists would come in and they just follow the instructions of build and run, and they're running unoptimized versions of the code, and obviously wasting a lot of resources. All right, map. So once again, map is our source code profiler, supports C, C++, Fortran, and Python now. Once again, very scalable in both the user interface and the architecture, and we'll go through a small example, hands-on example. But I just like to highlight what I think are some of the greatest strengths in our tools. So memory usage, this is a great way of detecting memory problems without using the debugger. You can see if there's like a jump in memory, it might be a red flag that there's a memory leak or misusage. Detecting imbalance in MPI, especially as you move to larger scale, that can be a really difficult problem to detect issues of not using all of your processes in comparable magnitudes. IO issues, once again, first step on the performance roadmap. IO problems can be orders of magnitude of lost performance, so definitely a good starting point. OpenMP, so both our tools support multi-threading, most typically OpenMP in HPC, but also native POSIX threads. Memory issues, and of course, get the last step on the performance roadmap is indeed vectorization, and every generation of processor that is getting more important. But once again, I want to highlight, make sure you've checked each of the previous steps on the performance roadmap to make sure that things are running best. So the architecture in MAP. So MAP is a sampling profiler. It does not require any instrumentation in your code. You just need to build with symbols. And also you want to make sure that you have optimization turned on at whatever level you intend to deploy at. And kind of the advice that I've been giving the last couple of years, and this is just following the observance of major labs, is most compilers these days, the overhead for including symbols is extremely low. Virtually no overhead in performance and very low overhead in memory usage. So I recommend that both your release and debug builds include symbols, especially as you're moving to large scale. When you get a core dump or crash, if you don't have symbols, it's going to be hard to detect any problems at all. But if you have symbols, there's a much better chance that you can bring up a core file for an unexpected crash and be able to figure out the problem. Python, so Andrew and I's favorite new feature. So just want to highlight our Python. So we've support debugging Python and profiling Python. And so this is a screenshot of a Python run. And we really are focused on what I call HPC Python, uses of Python where you're using multiple processes in kind of a single process, multi-data type of architecture. So all of the processes are doing similar work. Our tools are really designed and optimized for that type of architecture. So if it's a single thread Python, or if it's Python where the different processes are doing different work, the tools will work, but that's not what we're focusing on as a real strength. The real sweet spot is if you're using something like MPI for Pi to data distribute your problem, the tools are going to work great. So our remote clients, especially in the last year, I really like to highlight this, where most of us are working at home and lots of us don't have the best network connection to the cluster that we might have if we were sitting at work. The way to run our tools is you install a client on your desktop, and we have clients for Windows, Macintosh, and Linux desktops. So you install the client on your desktop, and then it just uses an SSH tunnel to your cluster to run the tools on the cluster. So particularly with these days when we're working, this is the preferred way overall, but especially these days when we're working at home. So you get to trying the tools. I have the link here for how to set that up. It's pretty straightforward. One other kind of work from home focused capability is what we call offline debugging, and I'll demonstrate this today. It's kind of one of my favorite growing features is being able to run the debugger without the user interface, and the job just runs as normal and it generates an output file. So for cases where it takes a long time to reproduce the problem, or it's kind of non-deterministic and you don't know the nature of how it's going to come up, this is a great way to debug. And once again, especially when we're at home and things are not really reliable on our connection, this is a great capability. Okay, so I'm going to get into a hands-on demo with DDT, but any questions kind of at a high level before we get started with that? Okay. Okay, so I'm just running on my local system here in a Linux VM, but the typical workflow is integrating with your batch system. So you would start up your remote client and then go to log into your cluster and start your job from there. And you'd submit your job as you normally do. When your turn comes up in the queue, it would connect to the remote client. So we'll circulate some after meeting stuff that goes through the details of that, because most realistic working situation, depending on how your site is set up, is you obviously have to integrate with the cluster. And there's a few steps of doing that, but it's pretty straightforward. Okay, so I've got a C program here that I'm going to run with 4 processes. It does not have any threading, so I'm not selecting OpenMP. And I'm in the wrong directory. Okay, so it's connecting to the DDT daemon that's dispatching jobs to each node on the cluster and starting up the processes on each node in the cluster. So even at my small scale of 4 processes, it takes a moment. Okay, so let's go through the user interface a little bit. At the top, we have operations for running processes, pausing, stepping into blocks, manipulating the stack frame. Oh, forgot about a new one here. So recently added the ability to disassemble and see assembly mode. And it's kind of interesting just from a development point of view. This is becoming more important as we're seeing more architectures out there. When everybody was running x86, it was a little bit less used, but it's interesting. We have a lot of field engineers who are working with customers that are getting their x86 codes, things like WARF and GROMACS and NAMD, very large codes, going on ARM. And it's often helpful to be able to see disassembly on a different architecture to detect either accuracy or performance problems. Then controls for manipulating the processes. So I can hover over these little blocks. You see the process ID for the selected process. On the left-hand side, kind of a navigator, something like you might see in an IDE like Visual Studio or an Eclipse plugin. Source code view. And once again, static analysis I mentioned, it'll show a little roadside warning type of sign. If you hover over that, it'll give you some information about potential problems. Like I said, this is a semantic analysis, so it's not necessarily a problem. For example, executing we have an issue here of not freeing memory, but it's the main, so it's kind of sloppy coding, but it's not necessarily a problem. Then a view for variables. So we can hover over variable, get some information about its definition, or if it's been instantiated, it'll actually show the value. So let's step along a few lines so we can look at that closer. Oops. I ran all the way to the end, so I want to restart. So this is particularly important when you're running on your cluster and it's a situation that submitting your job might take a while to get your turn. Within DDT, you can restart your debugging session without having to go through the batch system again. So if I was in a queuing system here, I could exit main, resubmit main, resubmit it to the compute nodes and run without having to submit in the queue again. Okay, I hit play, so it ran all the processes to the end. What I really want to do is I just want to step along statement by statement, instantiate a few variables here. Okay, so now if we go back to the variables view, we can hover over value and see that it's been instantiated. And then to the right of it, we have a little chart, a sparkline chart, where it's kind of a plot of the value of the variable across all the processes. So easy to see with rank. For example, my rank will typically range from 0 to n-1, and we can see that in the shape of the plot. So once again, part of our scalability is you can run this sample on hundreds or thousands of processes, and the chart will appear the same. So for example, with my rank, we're going to always want to have this monotonically increasing curve, and it's easy to spot problems very quickly. And we can bring up a detailed view and see the actual values and get some statistics of the variable across it. We can export it to a spreadsheet or an HDF file. Okay, breakpoints. So breakpoints are the ability to halt execution at a location. And in DDT, we have a lot of flexibility about how to do that. So I really encourage you, especially when you're getting started, to bring up the dialogue and use the dialogue for breakpoints, watch points, in that it's kind of self-documenting of how to do things and what can be done. And we give a lot of flexibility to really focus your search. So in-depth tutorials, one thing we really kind of try to focus on is using a methodology of, in your debugging, when you start out, form a hypothesis, and most people in HPC kind of come from a science background, so this is all natural stuff. Of form a hypothesis of what the problem is, and we even have a logbook, much like the scientist would use, where you can log your hypotheses, and it keeps track of it in this HTML file. So make a hypothesis of what the problem is, and then as you're searching for it, try to focus as much as possible the debugging in a couple reasons. In that, if you can focus it to a certain subset of the run, it's going to be a lot less data to sort through, and it's less overhead on the debugger. So we can set it for line location or function entry point, for a specific process or process group. So for example, if we know that the problem only occurs in a given process, we could set that. Or for a specific process group, we can define a set of processes and limit it to that group. So for example, in the climate type world, we'd often have part of the model focused on the atmosphere, part on the ocean, perhaps part on the boundary layer. And typically problems would only occur within part of that domain. So a way to focus your search. Hit limits, only looking a certain iteration or on a conditional. So very common cases, the problem doesn't occur until after like ij, k, iterate, or whatever. And if you know that's the case, set a conditional so you have less data to sort through and reduce the overhead. But I'm going to set it for all processes unconditionally at line 112. We hit play, and we see that it advanced all 4 processes to that line. And we can hover over this blue line, so there'll be a blue line for each process where it's stopped. In my case, all 4 processes have stopped on 112, but as you get larger and more complicated codes, when you pause, you're probably going to have situations where different processes are paused in different locations. Okay, so that's breakpoints. Let's go to trace points. So trace points are what I refer to as the scalable printf in the overview. This is the ability to output values from the debugger while you're running without having to rebuild. And once again, I recommend using the dialog. It's kind of self-documented what you could do. Similar to breakpoint, you can set this for a specific line location, function entry point, limit the search to a specific process or process group. Then we need to output, choose the variables we want to output. I'm going to output the values of X and Y. Those are just kind of a loop control variable consideration. Once again, try to limit the domain if we can. So for example, maybe if I just need to get a high level view of these values, and say just output the data every other iteration. And then I'm going to run all processes past that block. And we can see the process numbers up here changing colors to show the status of each process. Once again, the blue line shows us that all 4 processes advanced to line 133. Then if we go to trace point output, we can see the values. So somewhat like a print statement, but much more scalable. So it shows the domain. And then once again, we use the Spark line similar to the variables view to show the shape of the variable across all of the processes. So much more scalable than a print statement. And you can get the output without changing the program, which also has the artifact of when you put in print statements, you often change the determinism, and you might have the issue of the problem migrates to a different area, or in the craziest cases, goes away. And as you move to larger scale, that issue of changing the determinism becomes more and more of an issue. Okay, so breakpoints, halting execution at a location, trace points, outputting values. Watch points are the ability to halt execution dependent upon the value of an expression. So once again, for a specific process, a process group, I'm just going to enter this variable name that's in scope right now. And we can say halt for read or write or both. I'm going to say halt on a read or write. Again, run processes. And it shows us that it halted on line 148, and it shows us the old value and the new value. So very powerful tool for cases where you get to a certain location and the state of your program is not as you expect, but you don't have an idea where things went wrong. It can be quite a ways upstream in another module, those type of issues. Watch points are a very powerful way to track that down.
Beau, I have a question. So
yes,
how does it integrate with job launchers on the HPC systems? Like we use Slurm here at TAC. So does it have any interfacing with that system or HPC? Yeah, HPC system. And for example, in scheduling processes, like what is the like if you're running a code, what is the approach which you take? Like, is it first come, first serve, or based on different processes, or you dynamically allocate the resources based on how fast your code gets completed or something like that?
So your job submission is exactly the same. So kind of the workflow is two steps here. So I'm not set up to connect to a real machine, so I'll kind of fake some of it. But let me show you how the workflow would feel. So in one terminal, you'll SSH to the login node of your cluster, and you'll edit your existing batch submission. So you go into your existing batch file and you'll prefix, you'll have like an MPI run or an app run type command with a bunch of arguments. All you do is you prefix the existing MPI run launch within your batch file with DDT, with the number of processes you want to run, and any other DDT arguments. Then you submit your job just as you would normally, and it will get its turn and start up just as it normally would. Now, the other part of it, though, is before you submit your job on your local desktop, you'll want to start the client. So install the client on your desktop, and you connect to it. So this is an NCAR machine that I have an account on, and I would connect to that machine, and it will sit and wait to receive a prompt from your job. So you launch this client, it sits and waits, and then when your job that you've submitted from the login node gets its turn and launches, it's going to connect to the client and say, hey, you've got a job that wants to connect.
Interesting.
So I've glossed over a lot there, and that's actually going through this requires me to connect to a system and takes a little bit, but we will circulate some stuff afterwards that goes through it. It's pretty straightforward. It's just you got to install the client, then the site that you've connected to has to be set up. But that's the preferred way to connect to a real cluster.
So interesting. So for for example, we like to run a code on TAC, we have to write a specific bash script. So I was wondering, like, how are we supposed to do it with ARM? Like, are we supposed to run the code directly, or we can also write a bash script and then run it through ARM?
So all you should have to do, and there's certainly a lot of codes out there that have a lot of scripting before they actually launch the job, is somewhere within your script or your set of scripts, there's going to be a line that does MPI run or app run, probably MPI run at TAC. Is find the line that actually launches the job, which is going to be MPI run something something, and prefix that with DDT.
Cool.
So if you have a problem with that, let us know. Especially so TAC is a big customer, and there's a lot of usage there, and there's probably even people that might be familiar with your exact application. So if you have problems with that, let me know, and we can get it going for you.
Sure. Thank you.
And also at TAC, I believe, Andrew, you're probably more familiar with this. I believe TAC has an ARM specific page of exactly how our tools work at TAC. Isn't that the case?
I believe so, but I'd have to check with John.
Yeah, we'll track that down afterwards and send and circulate the page, because it's been a while, but I'm pretty sure every site has unique aspects about how things are run, and there's usually a site-specific page of what you need to do, and I'm pretty sure they've done that. Our tools are well supported there.
Cool. Thank you.
Okay, so that's kind of highlights of DDT interface, and one I would like to go through is the offline debugging that I mentioned. Let's actually walk through the process of offline debugging. And there's a lot to this, and in the after notes that will circulate, I referenced some blog information. I've done a couple of blogs on this that go into details of all the different ways, or a lot of different ways that you can use offline debugging. And once again, this is really a very powerful tool. A couple other items actually overlooked, and while we're talking about clusters, is a couple things within the code view is so you can actually edit the code within the user interface and rebuild it. So for cases where you have just a kind of a minor edit and you want to rebuild, and it takes a while to get your turn on the cluster, this can be very useful in that you can rebuild the code, redispatch it to the compute nodes, and launch the new executable again on the compute nodes without having to give up your space on the queue. So if it's just a quick edit build and you don't want to take a long time for your turn in the queue, this can be a useful method to do that. Okay, back to offline debugging. So offline debugging is the ability to use the debugger without the user interface. So once again, for cases where the most common are very large jobs where it might take a long time to get your turn in the queue. One of my favorite success stories was we had some folks at NCSA that had a bug outstanding for a long, long time, and it required almost the whole machine to reproduce. Very hard to do interactively. They set up an offline debugging session, and the first run found the problem. So large-scale bugs, non-deterministic bugs where it might happen in minutes or it might only happen once every 100 runs. Offline mode can be a useful way of getting a lot of data for that. Or for cases where it just takes a really long time to get your turn in the queue and you don't want to wait till the middle of the night. So there's a few ways to do this. You can give arguments to the program. My preferred way, especially for relatively modest, is to use the interface to set up your experiment and then run it from the command line. Okay, so we have a breakpoint on 111. Let's change that to something else.
If possible, can you increase the font size, Beau?
I can increase the window size here. Let's see if this is that any better?
Yes,
Not much.
that's better. Yeah, that's better. Thank you.
I know what you really wanted. We don't do that very well, is to literally make the font of the code a little bigger. Okay, so I got a few breakpoints. Let's go back to this trace point we had. So I still have the trace point that I set in our previous run. It's just going to go to a file. So let's output it on every iteration, output the values of X and Y again. We still have the watch point. Let's leave the watch point. So now what I'm going to do is I'm going to go to File, Save Session. This is just an XML file that is going to tell the debugger what I've requested. So to set up this session file, you can run it at very small scale. The typical workflow is create your session file on the login node with just a couple processes because we're not actually running in earnest. Then we exit the tool. And then we submit from the command line. So we say dash offline. And then specify the name of the file we just created. And turn on memory debugging. So I recommend definitely with offline runs, always turn on memory debugging. And if you select balanced, it's relatively modest overhead, like less than 5%. So even if you're not looking for a memory related problem, may as well get that data. There's really no additional overhead. And also in development mode. So a lot of sites now will use the tool kind of as an IDE. So even when they're not debugging per se, but just run within the IDE with memory debugging turned on. So even if you're not looking for that type of problem, memory bugs can often be latent for a long time. And the sooner you find them, typically the less expensive they are to find. So kind of use the IDE as a memory debugging tool. Okay, so then I'll specify the processes. Now at this point, when you're running the batch system, everything I've highlighted here would then be followed by whatever you already have as an MPI run in your existing batch file. So just go into your existing batch file, as we did in interactive mode, prefix the MPI run with all that stuff I just typed. Then submit the job as normal. Start up the client on your desktop. Or I take it back, you don't even have to start the client, we're in offline mode. But I'm running interactively here, so I'm just going to give the job. Okay, so now the job is going to run as normal, creating .out.air files, depending on how your Slurm setup is running. And then in addition, it will generate an output file, a DDT output file. And by default, this is an HTML file, which is very verbose, and for smaller runs, it's a nice way to navigate. But for large jobs where it's collecting a lot of data, you've done a lot of instrumentation, much more than you might be able to do interactively, you can also create it as a CSV file. And in the material that was circulated in the blog file, I go into quite a bit of information about how to use it in a CSV mode, where it's, it's a lot more compact and a little easier to post-process with things like sed, grep, and awk. Or I guess the modern thing would be with Python. Sed, grep, and awk, kind of old school. So once again, the nice part of this is, like, for a large run where it's taking a lot of time, I can just submit it, and if it might run in a matter of hours or even days. I mean, a lot of very large scale problems, of course, it takes days and days before the job will even run. Okay, So it chose a name for us there. We can open that up in our favorite browser. Okay, so we have an XML file, and much like the logbook within DDT, we can see it shows us the time of the start, the build date of the executable, and then output information at each point where it hit a breakpoint or watch point. So what I want to highlight is it obviously doesn't stop at a breakpoint or a watch point. The name is kind of overloaded in this context. When it reaches the breakpoint or the watch point, it outputs the state of the program. So we get to see the value of the stacks. So a lot of information. So even for this quite small run with not much instrumentation, we can see that we can gather a lot of data. So you can envision for a large run where you really don't have a good insight of the nature of the problem, you can put in a lot of instrumentation and get a lot more information and a lot more robust information than you can within the user interface. Now, the one caveat to watch is even when you do this as a CSV file, you can envision you're generating a lot of information. So make sure you're on a partition that has a big file space. So a lot of details. And then the trace points, once again, very similar to the appearance in the user interface. But I did it for every iteration through the loop, so we see we gather a lot of details. Memory usage report. Now this program doesn't really have a memory leak per se, but we can choose sections of the run to see the function called stack to that point. So you can envision if there is a section that was leaking memory, it gives you a nice visual way to navigate that. So one other thing on memory debugging, kind of want to point out is Valgrind. I don't know if you use Valgrind, but I've been a big fan of that tool in the past, and it does a very good job of giving this kind of information.
Yeah, we have used Valgrind in one of our courses, so most of us who have taken that course have used it.
Okay.
Yeah, for code coverage. Yeah, and memory. Yeah, memory leak. Sorry. Yeah.
Great. So yeah, no, I'm a big fan of that tool, but if you've used it, you've probably learned that it can have a lot of overhead for a significant run, and it gives a lot of information. But if you're pursuing that type of problem, I just encourage you to give it a try in the debugger first, and that it's very low overhead, and there's a good chance you can find that type of information. Now, if you can't or you need more details, once again, Valgrind's a great tool, but it is a lot of overhead. Okay, offline debugging. So once again, we'll circulate some stuff. It's as I put it to Andrew, my favorite up and coming feature, even though we've had it for like 10 years. And that as we move to larger scale, debugging techniques kind of change a little bit, and using the user interface for a lot of larger scale bugs is often challenging. Okay, so I talked about memory bugging a little bit in offline mode, just to kind of quickly go through that in the user interface. I don't think I touched on that yet. And same work process, see example, no threads in this case. So one thing I wanted to highlight, I don't have an example for today of OpenMP, but the user interface in OpenMP looks and feels the same as processes. So you navigate processes with these rectangles at the top. If there was multiple threading, there would be an additional line with ovals where there would be n ovals, where n is the number of threads you're running, and you could navigate among the threads just like we do with processes. So we can see we're now on my rank 1. We see that changing the locals tab. If we were running with threads, it'd be exactly the same. memory debugging. So a couple tools for memory debugging. I don't really have a memory bug to walk through today, but just to highlight the tools, because these are very useful when you're looking for that type of problem. Oh, I didn't turn it on. So one more step. So by default, memory debugging is not turned on in the user interface. So you got to select this block. And these are just kind of the defaults that I recommend. So when heap debugging, there's a whole bunch of different specific things we can look for. Obviously, the more of them we set, the more overhead. Just empirically, I found if we set it to balanced, it's a set of defaults that catches most issues. It's pretty rare where that level has not trapped a heap issue, but yet the overhead is relatively modest. Guard pages, this is the ability to detect reading or writing outside of an array. And heap consistency, once again, these are just my kind of empirically over the years of defaults that I found to catch a lot of things without too much overhead. Because the trade-off is, if the overhead is high, you're not going to want to use this when you're in development mode. Once again, I kind of recommend when you're in development mode, just use the tool as an IDE with memory debugging turned on, and as your edit, build, rerun cycle is going, you'll catch memory problems much quicker. Okay, so I've got memory debugging turned on, yeah. Okay. All right, so there's essentially two tools for looking at memory. There's memory usage, memory stats. So go to tools, memory stats, memory usage. I like to start with memory stats. This is kind of a high level view. Just gives information on the amount of allocations that have been made, the number of calls that have been made. And this is also information that's cached within the login daemon node that's running. So when you're running at scale, this is very quick. You can bring it up and it's going to instantly give you this information. So if there's like a process that has an outstanding amount of allocations, it's going to jump out very quickly. And then typically the next step would be to go to memory usage. Now at this point, it's going to go out to each compute node, each process, and query the kernel about the actual functions that have done the allocation. So you get a lot more rich data, but it's doing a little more work and some more data to sort through. And so we can see from the legend here which processes are allocating, and we can click through to see the history of those allocations and navigate to the source code for those allocations. Okay, so that's certainly not everything. Once again, I kind of focused on a few of the things that I think are most useful or most powerful in DDT, but definitely a lot more. So at this point, it's going to move on to our performance tools, but any questions on DDT before we do that?
I'm curious. I mean, DDT is so powerful, but are there any like precursors or any other tools apart from DDT which are there in the industry? And although we have seen, but like, can you talk about how DDT performs or outperforms all of them?
So the number one competitor, and has been there forever, is the print statement. And so that's obviously kind of our biggest competitor. And I'd say, there's a lot of folks where when you have a bug, the first temptation is to use a print statement. In that, I think, unlike a lot of development tasks, most development tasks, like if you're going to write a script in MATLAB or something, you have a vision in your head of the task and what's involved. With debugging, it's always our first instinct to say, oh, I think I know what this is going to be, and I'm going to put in this print statement. I'm going to find the problem in 5 minutes. And lots of the time that's true, but sometimes it's not, and you can go on for hours and days trying to find the problem. And if you start with tools from the beginning and a systematic approach, so like I mentioned, make hypotheses of what the problem is, bring up the tool, be it DDT or another tool, and use the proper features for doing that. So biggest one is print statement. So no matter how trivial you think the problem is, use your debugger, whether it's DDT or the Python debugger for a serial Python, is another one. Now, in terms of commercial tools, there's another company, TotalView, which has been around for a long time also. In fact, when I was at NCAR, that's the only tool that we had. And I literally didn't learn DDT till I came to Olivia/ARM. So TotalView is another tool, and there's certainly usage of that. I think our big strength relative to TotalView is DDT was designed from the ground up to be really focused for HPC type of applications running at scale. So everything within the user interface is really optimized for HPC type of codes. And DDT is very efficient with that. As I mentioned, we've been used in literally hundreds of thousands of processes, and the tool works smoothly. But in terms of commercial, TotalView is one other one. That's pretty much the only other commercial option that's available.
Sweet. We have two people who raised their hands. So I'd like to go with the first one first.
Yes.
So Meghna, would you like to ask a question?
Hi, Boo. That was a very nice talk about DDT. And I have two questions. Firstly, is this available for everybody? Is it free? And can people use it directly? And second question is a bit more specific. I know you talked about how DDT can be used with MPI and OpenMP. You might already be aware of this other kind of parallel system called Launcher at Attack, which does like different runs for different parameters. So we have the command called param run. Does DDT work with that as well? Would be my questions.
So easiest ones first. So your second question about Launcher, I've heard about it, that Attack, and I'm guessing we do because we probably would have had somebody complain about it, but I will have to follow up of our status with that. So for better or worse, TAC has a great support team, and they do a great job of supporting our tools. The downside of it is we don't hear a whole lot about things going wrong, and that they tend to fix it themselves. So I'll have to look into that question for you. In terms of, quote, free to use, so any sites that you have an account on that you're using where we're licensed, and we're licensed a lot. We have a large license at TAC, so if you're working at TAC, the tools are certainly available to you there. We're available at most of the NSF labs and DOE labs. So places like Argonne, NERSC. So NERSC is a big DOE lab that has a lot of usage and very big license. NCAR. So essentially, if our tools are licensed at the site where you're working, they're there for you to use. So if you have a specific site beyond those that I mentioned, we'd probably have to get Andrew's help to let us know if you have a license there. But if you have a question on that, we can, if you have a site beyond one of the main ones I listed, let us know what it is, and we can let you know if you have a license already. Now, beyond that, if you want to try the tools on your own setup, we have like a trial version. We could run for a few weeks if you want to like set it up on your own thing to give it a try.
Sweet. Thank you, Beau.
Yeah.
Next one is by William. William, would you like to ask your question?
Yeah. So I write a lot of HPC Python, which is usually a combination of like pure Python, Numba, some JIT compiled functions, and a lot of like Python wrapped like C++ and CUDA kernels. How does DDT kind of interact with some kind of like multi-layered approach there? Do you actually have all like the debugging symbols? Because from my experience, it's usually a mess, and I've kind of reverted to using print statements or just attaching GDB to an MPI rank and seeing what happens.
So no, that's a great question. And so two parts of Python. So we've been supporting Python in profiling for a couple of years. And as long as you have symbols of the compiled code part, everything works pretty straightforward. is relatively new within DDT. And if you don't have so debugging the Python part, obviously there's no symbols involved, but all of the capability we looked at, most of that pretty much works. So setting breakpoints in Python code, looking at variables, seeing the spark lines of Python variables across processes all works. Watch points, so once again, watch points is a hardware thing, so that doesn't work in the native Python part of it.
Yeah.
Now, in terms of the LinkedIn part, realistically, to get interesting information, you need symbols. But the reality is, if you're using a mature toolkit like NumPy or Pandas, the problem is probably not in that code. It's probably
they ship the binaries without the debugging symbols.
They do. You can get that set up, and we've gone through the exercise of doing that. But one thing kind of learned from the exercise is we've never found a bug in NumPy. I mean, the problem is usually you've called the toolkit incorrectly. So in terms of technique, the best that I can recommend is set breakpoints at the boundary layer of where you're going into the toolkit, and have a look at variables and verify that you are calling the toolkit with variables as it expects. And then also set breakpoints when you exit from the toolkit at the boundary layer of the native Python, and see if the results are what you expect. And realistically, that's where the problems are occurring, is you're making calls where the variables are not as the toolkit expects, or the data in the variables. Right. So I agree with you. Yeah, it's whenever you mix languages, it does start to get more challenging. But realistically, the bug is not in NumPy. Not typically.
No. I was talking more about like the Numba, which is the just-in-time compiler now for Python.
Yeah. So once again, in DBT, this is relatively new. It's just in the last couple months, and so still learning a lot about it. But to the extent that I played around with so far, I mean, it definitely helps a lot, especially just basic things of setting breakpoints, seeing variable values with multiple Python processes.
Okay. Thank you.
All right, Mohammed, is that it, or should we move on to performance stuff?
I think if you want, we can go ahead with the performance stuff for a little bit, but I would say, like, if you talk about HPC prospects and skills required for using DDT and Forge, I think that would help people a lot more. Yeah,
I'll move on to that pretty quickly. And I forget, are we budgeted to 11:30 my time or noon my time?
I would say like we can go for like 20-25 minutes more. And with that, I have there's one more question in the chat from Jonathan. He's asking, for most non-scale related debugging, I run toy problems on my local machine instead of burning TAC hours. Are there student licenses for this purpose?
There is a workstation license. I don't think we have a student license per se, do we, Andrew?
No, we do not. But if there's a specific need, reach out to me. TAC has a pretty substantial license installed, and I'll work with you on getting a license for a period of time. So if there's a specific need, please contact me directly. Mohammed, you have my details, so feel free to.
Sure, I will share it with you, Jonathan. Two more quick questions from YouTube. So it's from Evan. So he's asking, what is the overhead of DDT in addition to the print statement? And are there any tutorials or short courses for ARM Forge?
Yeah, great. So the overhead varies a lot on what you're doing. So for example, trace points are writing something to a file. So much like a print statement, there is overhead involved. And in terms of outputting to that, it's going to be comparable to a print statement. Now, once again, this comes back to focusing your search. So in the debugger, I kind of illustrated how you can focus your search by using the conditional or every other iteration. And by doing so, it's very, very easy to do that in the debugger, and that will reduce your overhead. But at a low level, outputting with the trace point, it's going to be writing to a file system, just like a print statement. So there's going to be comparable overhead. Now, in terms of other overhead, like memory debugging and things like that, in general, it's a few percent If you're writing very rich C++ stuff that has a lot of constructors and things like that, it can move up a little bit. But I always like to address that of if you're using that type of C++, it's not going to be the greatest performance HPC type of codes anyway. So sorry to be vague, but it's kind of varies. But in general, in most situations, most codes you'd work with, something like Wharf is going to be a few percent, that type of thing.
Sweet. And how about tutorials or short courses for
yes.
ARM? Yeah.
Thank you. I forgot part two. So yeah, we have there's a whole bunch of blogs. Like I mentioned, I have a couple long blogs on offline debugging. There's some short webinars, and we will circulate a document afterwards that references all those of we have quite a bit of online kind of both video and blog type of content to learn in more depth.
Sweet. Thank you, Beau.
Great. So I'll be real quick on MAP. So we have plenty of time for dialogue. So once again, into performance workflow, start with a performance report. I showed that in the overview. Then in terms of source code profiling, MAP is our source code profiler. So the workflow with MAP is go into your batch file on your login node, edit the batch file, and just prefix the run, your existing MPI run with map -- profiles, submit the job as normal, and it will generate a file that we can then load. So I'm going to just load a data file that I have previously generated. And once again, you do this with your client. So start the client on your desktop, connect to the cluster, and you'll be browsing the file system of the cluster. So the top of the user interface are several charts where the horizontal axis is the timeline of the run. And we gather about 30 various metrics. By default, it's just these three, but there's about 30 metrics that we gather data on. Then in the center is source code view. But next to each line of source code, we show a little chart that shows how the time is spent on that line of code. So for example, on line 10, we can see that 20%, the first 20% of the run was spent in that called imbalance, and some of it was in compute, some of it was in MPI. So the real heart of the workflow in MAP is using these charts to find potential problems. So for example, in the top chart here, we can hover above and see there's a lot of time in single thread compute, quite a bit of time spent in MPI, and that's always a red flag. MPI typically should be just kind of spiky patterns where each process is off doing its work. It comes to a boundary, does something, a halo exchange to its neighbors, and gets back to work. But my process is not. So I'm adding in MPI call duration. As we hover over that, we can see at about 1.2 seconds in, the values range from 0 to 890 milliseconds, so enormous amount of time. So definitely an issue there. So I'm kind of a whirlwind here, but the workflow is we highlight a section of this chart where there's a potential issue, and it updates the source code view to only show the data, the window that I selected. So we can see that 100% of my selected window is in this imbalance function. And then the way we kind of home in on that is we collapse all of the blocks of source code, and then block by block, we drill down trying to understand what's going on. So we can see on line 81, get a breakdown of how that block of code is spending time. And within a few nesting levels, we've narrowed it down to 2 lines of code, where about 60% is being spent on this computation line and almost 40% is on this reduction. And so this is a good case where we go back to the debugger. Like, we can study this code and it's not a complicated error, but going back to the debugger, we can step through line by line, and it becomes quite obvious the error is I'm iterating over a rank number and hence not dividing the work very well across all of the processes. So spending a lot of processes are spending time in this reduction. And then at the bottom, we have a kind of bottom-up view, something you might get from gprop. Shows time spent within functions, children of functions, time spent within threads. It showed it within processes and subthreads if we were using OpenMP. So kind of a whirlwind of map, but I just kind of want to show the heart of this workflow, because our real strength is being very easy to use, especially at larger scale. Well, we really focus a lot on like end user domain scientists that don't want to invest a lot of time in learning a complicated tool. For example, TAC has a lot of great tools of Tau, HPC Toolkit, some very useful HPC profiling tools, but to get good information out of them can be a pretty steep learning curve. And for serious performance problems, that's great and it's worth the investment. But MAP provides an alternative that's very easy to quickly find potential issues. So kind of a whirlwind, but the information that we're going to circulate afterward goes into a little more depth on how to use MAP. But it really is straightforward. Like one metric I like to reference is the user's manual for MAP. Forge is all in one user manual, but the MAP portion is about 50 pages total for everything. So it's not a complicated tool. Okay, so want a bunch of time for kind of Q&A, but any quick questions on MAP?
So is MAP like an equivalent of GCOV and LCOV that we use for code coverage?
It's not really a code coverage tool. It won't show you all of the lines that have been executed and the amount of execution. So no, it's definitely focused just on showing how time is being spent within your code.
Okay. I think we generally use Groovy Timer for that, to time the processes. I think that's what we use here at TAC. But that's interesting actually to get details about different processes with this GUI. I like the GUI.
Cool. Yeah, I encourage you to have a look at it. So once again, I believe TAC has a license for MAP also, don't they, Andrew?
Sorry about that. I was on mute. Yes, they do. Absolutely.
Okay, great. Yeah, so if you're working on TAC, you've got access to MAP and performance reports also. So yeah, give it a try. Great. So yeah, kind of HPC and more kind of career type questions if we want to move on to that.
Sweet. Thank you so much for talking about these points. I feel like some of us have left because our classes start at 12. So like this short window is when most of us came to the talk and
Oh, understood.
all this happened. So thank you very much for that. I was wondering, what would be your advice to aspiring computational scientists? Like which tools or which language is being most preferred in HPC industry, and what sort of skill sets should we develop in order to become better computational scientists in the future? Thank you.
Yeah, no, I totally get it. So just kind of give you some background. I came from kind of when I came through, computational science was not a thing per se, and my background was in mathematics and computer science. And then my first job was in an oceanography lab, and I didn't know anything about oceanography or climate or weather. And kind of over the years, my expertise is focused on kind of earth science. So oceanography, climate, weather, I kind of learned that on the job. My advice, though, is in the current generation of things, employers are going to want you to have some domain expertise. So, for example, we have field engineers now who certainly know math and computer science, but they've done studies in climate weather or astronomy or fluid dynamics / mechanical engineering. And my number one advice would be that's a great way to prepare is have a domain specialty of whatever it is, astrophysics, biology, is whatever big HPC thing is. Have a domain focus, but in your day-to-day work, the thing that's going to enable you to do your job is strong math and computer science skills. So, make sure that those are strong. And then in terms of kind of at a vocational level of, given that expertise, be prepared with C++, big time. I mean, a lot of early career scientists that are working on big new codes are C and C++, but also Python and Fortran. Fortran is here, and there's still a lot of new code coming out in Fortran, and there's actual new codes coming out in Fortran. So I'd say all three of those, at least be competent in those languages, and then be, at least competent in the tools like ours. Be able to say, you know how to use a debugger, and you know how to profile, and major profiling tools. At least, you don't have to claim to be an expert. Employers aren't going to expect that. But most importantly, they want to see that you are open and use that type of stuff. So be able to show a little bit of competency in tools. A lot of up and coming things of containers. Containers are important stuff. Be able to show that, not that you know all of them, but, understanding what containers are about. And there's some that are more prevalent in HPC than others. And, maybe kind of focus on those and show that you know how to work within that kind of environment. But kind of just the broad set of tools that are used within HPC, at least show a competence. But once again, it's like, first and foremost, in terms of, a lot of employers are going to expect you to show that, but the thing they're going to want to see the most is you have some domain expertise. So like in our field engineers, we've got guys that cover all that different stuff, so they can go into clients. If we have a client that is a CFD expert, we've got a couple guys that are, that's their PhD is in CFD, but they are strong math, computer science people is kind of the first and foremost. So that's top of the list. But tools, languages, beyond those languages, obviously there's a lot of others out there, but for HPC employers, those three are, especially C++. There's a lot of big projects coming out in C++.
Interesting. What's your take on Julia?
I think it's interesting and up and coming. I don't know how much traction it's going to be. We get a few customers that are asking about it. My personal opinion is Python is far more important, and I believe going to be far more successful in HPC, especially with some of the road forward. Microsoft has made it a big priority of how they handle memory and performance, which are both a problem right now in HPC. If you're writing native HPC Python stuff, the way they do memory is not very efficient. It's not very thread friendly. And as we're moving to architectures with lots and lots of threads per device, that's becoming more important. But I think that community is stepping up to it. So I think that's prevalent. But in terms of languages, so once again, core computer science, when you go into jobs, to be able to show that you can understand languages and work with languages. So for example, most of our staff has spent a lot of time, and that big part of my career was involved with like developing an interpreter for numerical computation. A lot of our field engineers have like good understanding of compiler interpreter stuff. Because just in day-to-day work, it's like, even if you're not, quote, a developer, but you're part of a development-oriented staff, understanding languages and how to do language solution type problems, it's useful. And also, if you understand that most employers interpret it, and I agree, is you've got strong computer science skills.
Sweet. Thank you so much. And I will keep them in mind. And if anyone else has any questions, please feel free to chime in.
Yeah, so I guess this is a little bit different than off-solves, but I guess I was wondering about your take about where you see, I don't know, HPC as an industry in, say, like 20 years, given like Moore's Law and all these things. If you think we're sort of coming up to Moore's Law, or if HPC will continue to grow at its, sort of exponential rate in the next 20 years.
I think so. I think there's some hiccups in that there's some very substantial codes that are reaching inherent design limitations. So for example, the bulk of my large scale experiences with WRF, and WRF is still a well done code, but the early design in WRF was hundreds or thousands of processes, and we're talking millions of processes. There's some inherent issues. And in climate weather, there shouldn't be. The way that most the physics, at least when we do it with physics, not ML, but when we do climate with physics, in theory, that should be able to scale much bigger, much bigger than what we're at right now. And there's certainly demand for that, being able to solve weather problems, on twice the time scales and 10 times the resolution. There's consumers for that. So it'll be desirable, but I think there's a lot of codes where there's going to be some hiccups and some how things are reworked. But fundamentally, I think it will continue to increase, especially as there's new consumers. As I mentioned, Python is bringing new consumers, like, the history professor that wants to do some computational thing. That wouldn't have happened 10 years ago. And as those people have access to this kind of resource, I think the demand will continue. And one I saw recently, I forget the exact number, but Hyperion or one of those kind of predictor type organizations made a comment that the amount of electricity that will be consumed by HPC in 10 years is like a couple orders of magnitude bigger than it is right now. And if they're doing that, I mean, there's got to be big machines out there, and the machines are getting more efficient in terms of computation per watt. So no, I think it'll continue to grow. And personally, one of the most exciting part is seeing new consumers. I mean, for the bulk of my career, it's been mathematicians, physicists, biologists. That's pretty much been the consumers of it, and I think that's going to expand a lot. Cool. Any other questions? You're on mute there, Mohammed.
Yes, I feel like my internet is breaking because I'm not at home, but yeah, if anyone has any other questions, please feel free to ask. Okay, looks like no one else has any questions. So with that, I think now is the time to wrap it up. So thank you very much. Oh, Evan, do you have a question?
Oh no, I just put my video back on to say bye.
Okay.
All right.
So yeah, thank you very much, Beau, for joining us. And
Yeah,
it was very insightful, both on the tools perspective as well as the the industry perspective. And I think it is going to help us all in being better prepared for the industry. And thank you very much for your time. Thank you, Andrew. And we are looking forward to the materials you'll be sending later on. Thank you so much for joining. And thank you everyone who joined us on Zoom, YouTube. And I hope you all have a nice day. And do check out our website, sam.odin.utexas.edu.